Hello everyone and welcome. Today I'm going to get you through the process of setting up and running the M2C solver to simulate the generation and expansion of vapor bubbles induced by laser. I will demonstrate this process using an example case of a pear-shaped bubble generated by a homemade laser. This video and figure show our simulation results of this example case. This example case is presented in section 4 of our preprint available at arXiv. Okay, before we begin, let's ensure you have all the necessary modules installed on your system. You will need Git to clone the repository, CMake to generate the make files. The M2C code uses the parallel data structure implemented in the PET-C library developed by Argonne National Lab. It also uses some numerical linear algebra routines in Argonne, so make sure you have installed this too before install our M2C solver. The code can also use some root-finding routines in Boost, so installing Boost is optional. The M2C code is open source and can be downloaded from GitHub. The detailed computational model and numerical methods are presented in these two papers. Okay. First, let's open a terminal, run the following command to download the M2C solver. That is git clone the GitHub address. Okay, then ls. Yeah, we can see the downloaded directory and then navigate to it. Here you can use git log to check the commit history. For this example, the commit hash we used is this one. Yeah, I also put this number in this slide. Okay, then create. Let's ls to see the code structure. Yeah. Users can read these files to check our implementation of the numerical methods. For example, you can open this laser absorption solver.cpp and .h to see the methods used to solve our laser radiation equation, and also the phase transition model. Our method of latent heat reservoir is implemented in this phase transition.h. Okay, if we check this file, we can see that here, this function transition. Yeah, we first compare the cell temperature to see whether it exceeds the evaporation temperature, that is this Tmax. If not, it just keep absorbing the laser energy, but if yes, so else. We move the additional heat here, the D, to the latent heat reservoir, this lambda. Then compare it with the latent heat of vaporization to determine whether phase transition occur. Okay, let's create. Next step is compile the code. So let's first do CMake dot to generate the make files. Yeah, you can use ls to confirm that you should see these CMake files. Okay. Yeah, then let's compile the code using make. Yeah, this part just to speed up this process. Okay. Yeah, this process will take maybe several minutes. Okay, then we see this message, build target M2C. Let's do ls to confirm that you will get this executable file M2C. Yeah. Okay, now let's run a simulation using the example case shown in this slide. Okay, you can find the input files required for the simulation under this download directory M2C, just cd the tests. There is one folder called Laser Cavitation Job 24. Two example cases are given in this folder. This example is under this whole YAG fine mesh. Okay, here three files are required as input: the input.st, laserpower.txt, and the laserprobe.top. Let's do pwd to get the path of this folder, and then you can go to any folder you want to put your results. Okay, here I just make a new folder called test here, and then navigate to it. Yeah, let's copy the needed input files. So copy this path, and then we copy the input.st, laserpower.txt, and the laserprobe.top. Yeah, let's do errors. Now we have these files. Okay, now let's check the input.st to see how to define your own input file for your specific problem. Just wait as input.st. Go to, here. First, users need to notice that units for all the variables in this file. In this example, the basic units are millimeter, gram, second, and Kelvin. All the variables should be transferred to the unit expressed as these basic units. The computational domain and the mesh partition are specified in this class mesh. Users need to first determine the size of the computational domain and whether the problem has cylindrical or spherical symmetry. For example, in this case, we adopt a cylindrical domain with a radius of 12 mm and a length of 24 mm. The simulation can be carried out on a two-dimensional mesh, leveraging the cylindrical symmetry of this problem. So here we set the tab to be cylindrical. X is the axial direction, so we have a length of 24 mm from x0 to x max. And Y is the radial direction, have the radius of this 12 mm. For the Z direction, we just give the minimum cell width from Z0 to Z max. Okay, then we need to specify the boundary conditions for all these 6 boundaries. In this case, we have this cylindrical symmetry, so symmetry boundary conditions are enforced on Y0, Z0, and Zmax. And for other 3 boundaries, we specify far-field boundary conditions. Okay, for the mesh generation part, this solver will automatically generate a Cartesian mesh using one of two options. The first one is specifying the number of cells along a direction. The second one is providing a series of control points with corresponding element sizes. If you specify in the number of cells along a given direction, for example, we give the numbers of cells along Z direction, the solver will uniformly segment that direction, creating equally sized elements. But if you providing a series of control points and their corresponding element sizes, the solver will interpolate the element sizes between these points. This allows for a more refined and customized mesh distribution, adapting the element sizes according to the specified control points. In this case, we give this interpolated segmentation method in X and Y direction, and the minimum element size set up to 0.0015 millimeter in the bubble region. Next step, users need to determine the number of materials involved in this problem and select the appropriate equation of state for each material. These are specified under this class called equations. Okay, in this example case, we have two materials, liquid water and water vapor. The Noble-Abel-Stephen gas equation of state is used to model both liquid water, this material number 0, and also water vapor, this material ID equal to 1. The parameter values required for this equation of state should be determined based on reliable references. You can check our reference in our preprint papers here. Okay. Yeah. Then if the problem involves material transition, users should specify this class called material transition to set the related parameters. In this case, we have transition from material ID 0 to 1 when vaporization occurs, that from water to water vapor. So the specified parameter values are here. So the from material ID, the to material ID, and the to threshold, that's a temperature upper bound, the evaporation temperature here, and also the latent heat for vaporization. This, the specified parameter values and also their references are provided in the manuscript. Okay, then next we need to give the initial and boundary conditions under these two classes, initial condition, boundary conditions. In this case, the computation domain is initially occupied only by liquid water with density to be 0.001 and the temperature be around 20 degrees Celsius and pressure here and the velocity here. And this initial condition also functions as the far-field boundary conditions for the simulation. So we specify a far-field boundary condition within this class, including the given density, velocity for all directions, and the pressure. The temperature can be computed using the equation of state and these states. The material ID is not specified in this input field, so the solver will use the default value, which is 0, so it's water in this case. So it's yeah. Then within the initial condition class, we leave it empty. So the logic is when a far-field boundary condition is specified and the user-defined initial condition is empty, the solver will use this far-field boundary condition as the initial condition. Alternatively, users can add a class called default initial state to define the initial condition. You can check the details in the file called iodata.cpp. The next part is about setting the laser. Okay, first, in certain laser-induced cavitation problems, part of the laser generator structure are situated within the computational domain, which will affect the fluid and bubble dynamics. For example, in this case, a portion of this laser fiber is included inside the computational domain. Our solver utilizes an embedded boundary method to deal with this problem, enabling the direct integration of the desired structure into the computational domain. So we need this embedded boundary method class to specify the structure. Okay, the important part is this mesh file. This file specifies the domain occupied by the laser fiber. So let's check this file. Just vi the laser probe .top. Okay, so in this part, we give the coordinates of all the constituent nodes here. And then this part just gives the domain of the laser fiber. Okay, yeah, create just keep this input.st. Okay, if there is no structure within the domain, users can just comment to this embedded boundary method or delete this class to deactivate this module. The properties of the laser beam are specified under this structure called laser. Yeah. Then let's explain each line. Okay, first you need to set the laser source power. The laser source power could be set as either a constant value using this source power or a time history from an external file. In this case, we have the mirrored experimental data here. So we use the laser power.txt file to give this time history. Let's check this file. vi laser power.txt. Okay, the first column is time and the second column is laser power. Okay, now, yeah. Okay, then we need to determine the laser source. Give the source center coordinate, this source center x, y, z, and the source plane radius, this source radius, and the laser beam direction. We use this coordinate to give the direction x, y, z. And we need to specify so now we specify a source plane that have a radius of this 0.1825 millimeter and proportional to the x direction. Okay. Now we need to give the spatial distribution of laser intensity in this source plane, uniform or Gaussian, this source distribution. If you use this Gaussian distribution, you need to specify this source beam width. It's here. Yeah. Additionally, determine this is a parallel, diverging, or focusing beam by this focusing angle. Negative means diverging, positive means focusing, and 0 means parallel. We also need to determine this range along the laser beam direction, which should be enough long for laser propagation, but do not exceed the computational domain boundary. Okay, another important parameter is this absorption coefficient for each material. You can see we have absorption coefficient for material ID1 and ID0 and ID1. We just give these values based on references. And this part is parameters for the numerical methods to solve the laser radiation equation. This alpha determines the flux method, either to be 0.5 or 1. And these three are used in the Gauss-Seidel method to solve this linear equation system. Okay, after you configure the laser type and the laser domain, as this example, you can adjust these parameters above to suit your specific problem requirements. With all these required parameters, we can now specify the numerical methods under space, multiphase, and time. Okay, it includes the flux methods, this reconstruction methods for Navier-Stokes equations. Okay, here is the reconstruction, and also the level set part. Determine which material you want to track. Here we track the water vapor, and whether you want to use the narrowband level set method and the reinitialization part. Under the time class, we can set the time integration method. Here we use Runge-Kutta 2 and give the CFL number or the time step size. And you need to set the max time for simulation. Here we set it as it's around 160 microsecond. Okay, in this output class, we can we need to first give the results folder name, then what to be output. Here we output all the variables, include velocity, level set, material ID, laser radiance, temperature, pressure, and density. Users could also use this probe class to output the state time history at fixed points. And you can also use this class called energy integration to integrate the required energy under this specified region. Okay, let's create this file. Then let's make a results folder as defined in the input field. Just make dir the results. Okay, then just run this code using this input field. Here I just show example of the command we use in Virginia Tech cluster. It's MPIEXEC to give the core number we want to use, and then the path for this executable file and M2C. And then we have this input.st as the input. And we output the screen part to this log.out file. Okay, let's do this. Yeah, you can see this screen output. Due to this fine mesh, it may take several minutes to get the time step size and the step informations. So let's just create this process. Okay. Yeah, you will see this logo and then some useful informations for mesh and the laser part. After you finish the simulation, just go to the results folder. Yeah, and you will get the solution in VTK format, which can be directly visualized using ParaView and other visualization software. And let's go to our example. Our example folder, just M2C tests, laser cavitation, and the whole file mesh. Yeah, here we have a folder called results. You can go to this folder. We give several images here as the reference solutions. Okay, yeah. Okay, thank you for your attention. This concludes the step-by-step guide on setting up and running the M2C solver. If you have any questions or need any assistance to use our solver, please feel free to contact us. Thank you.